Thanks, Frank. Thanks for everyone for coming. And you guys can all hear me in the back, right? Sounds really loud to me, but okay, you're waving, so I guess that's good. Again, as Frank said, my name is Joe Grand. I run a company called Grand Idea Studio. I'm an electrical engineer. I'm just a chronic inventor. I build devices and I sell them. Consumer electronics, video games, toys. Why I'm up here speaking at Black Hat. In a previous life, I was a member of a group called The Loft. Some of you might have recognized the name Kingpin. When I was involved in The Loft and was doing a lot more security, I had looked at a number of portable devices, authentication tokens, network-related devices, and looked at those devices for security problems, for any sort of design flaws on the hardware side of things, where for the past 10, 15 years, everybody really seemed to be focused on the software side, on the network side. So I come from a different school, and I love tampering with hardware and physically manipulating hardware. So that's what this talk is basically about, is some historical attacks that I've been involved in, and obviously there's many more, but this just touches the surface on a number of different hardware vulnerabilities, and we look at classes of attack and things like that. So also to keep your attention, I am giving away a copy of my game console hacking book, which is a book about hardware hacking and modifying video game systems. I'll give it out to whoever has the most relevant, best question at the end of the talk. So if you stay awake and think of something good to ask, then maybe you'll get the book. And of course, there's more outside at the bookseller. So anyway, the goals of the course are pretty straightforward. What I want to do is run through classes of hardware attacks. So we'll look at a number of different products, and even though you could basically pick any hardware product out there, just like you can pick any software product out there, and find a security problem with it, find some sort of exploitable issue or problem or bug, we're going to look at just more general classes that sort of seem to be a common role across multiple devices. Learning from history is really important, so you can actually take a look at prior attacks instead of recreating the wheel and relearning, which is something that we see a lot, both in the security industry, in the political world, in government, everywhere. It seems like learning from history is sort of forgotten about, and people just run into the same brick walls and run into the same problems all the time. So if you're new to the security field, or you're new to the hardware field, then looking at these types of attacks is important just to understand what people have done so far. Of course, we can also apply some of this knowledge to the newer devices that are out there. So even though some of these attacks might be a few years old, though some of them actually are a little more recent, we can take what we learn here, apply it to newer devices, which is hopefully something that I'm trying to transfer over to you guys so you can run back to your lab and start tweaking stuff. And the final goal is, as in any type of security, hardware-based security is extremely difficult. Arguably, it's harder than software-based security because with hardware devices, you can't just run out and apply a patch a lot of times. With software, you might be able to upgrade all the systems in your infrastructure. If you have a USB token or some sort of PDA or mobile device or some other piece of electronics that's deployed all over, it's a lot harder to upgrade those. So just because it's a hardware product, a lot of times people inherently think, ooh, it's hardware, it's a black box, it's installed in our rack, it must be secure. It's not, and hopefully this presentation will be a little bit of a wake-up call. For those that have attended one of my hardware hacking training courses that I do at Black Hat and at other places, some of these examples might be familiar to you, and now maybe after experimenting with some of the circuitry, you'll be able to understand a little more about how why they're as bad as I say they are. Also, I do want to let you guys know, sort of apologize for the ugly-looking slides in the proceedings. I have no idea what happened with those. That was out of my control. If you do want a nice set of slides that actually you can read all of the text and read the links, please just send me email. They might actually be on the CD that you'll get from Black Hat later, but there's no point in looking at the slides if you can't read them. So threat vectors, what we're going to do is look at, before we get into really the meat of the presentation, we're going to look at some of the vectors, different ways that people attack hardware, some of the goals of attacking hardware, why hardware would be attacked. Then we'll look at a bunch of different examples of network types of applications and hardware devices that have been broken. So interception or eavesdropping is more of a passive style of attack where access can be gained from a device without opening the product, so through some sort of external interface. So instead of having to actually modify hardware at all, you plug into the USB port, you plug into some undocumented JTAG connector on the bottom of the device, and I'll get into what that is a little later. So basically, it's some sort of passive thing where you're not physically attacking the device. Interruption or fault generation is more of like a denial of service type of attack, where you're preventing the product from functioning normally. It might not really be that useful a lot of times, depending on what you're trying to do. Obviously, if you're trying to retrieve data from the device, a denial of service and interruption might not work, but fault generation might. And fault generation sort of falls under the same thing because it's causing the product to do something that it wasn't intended to do normally. So whether we're varying temperature, varying a clock speed, varying some other environmental condition using X-rays to try to induce some fault and have the product fail in some way. Modification is the third vector here, and that's the most fun to me. That's opening up a product. Obviously invasive. You're tampering with the product, looking at circuitry, probing circuitry, adding components, removing components, cutting traces, doing what you need to in order to break the system. And then the final one's fabrication, or a type of man-in-the-middle attack. I give an example of some of Bunny Huang's work when he worked on hacking the Xbox, where he had actually fabricated an external circuit board to monitor some traces on the hypertransport bus, which was really cool. So some sort of man-in-the-middle attack on the network, sort of the same type of thing in hardware, creating maybe counterfeit assets, counterfeit data of a product. So maybe putting your own keys into a USB authentication token, for example, which we'll look at. Attack goals, obviously this depends on why somebody's attacking your product or why you want to attack a product. Competition in cloning seems to be really a big one for hardware. Somebody analyzing your device, ripping off your device, trying to get intellectual property out of it, some custom algorithms, any sort of trade secrets that might be useful to gain a marketplace advantage. This happens a lot of time with U.S. companies that have their products manufactured offshore. These manufacturers offshore might either give information to a knockoff manufacturer, somebody that can manufacture devices for cheaper, sell them on a gray market, black market, that sort of thing. Theft of service, obviously stealing cable TV, cloning cell phones, getting things for free that normally cost money. Again, it's a popular type of attack because a lot of times people don't like to pay for things. User authentication or spoofing. In the network world and the security world, this is an extremely important one that we show a few examples. Forging a user identity to gain access to a system, to basically prove you are who someone else is. Just sort of an interesting one. And then privilege escalation, gaining root, feature unlocking. There's a lot of devices that have some sort of backdoor debug mode, diagnostic ports, things that we could take advantage of to learn more about a system. Unlock these hidden commands is really cool, and there's a few examples here, but basically manufacturers like to make it easy for service personnel, for the manufacturer themselves to learn about the system, and that's something that we can take advantage of. So thinking like an attacker is something that's really important when we're looking at hardware, either from an attack point of view, if you're doing some sort of product analysis for a consulting firm, or if you're on the design side of things. You really need to understand what you're protecting, why you're protecting it. Here's a pretty cool picture from a guy named Paul Kocher, who's a really well-known hardware-based security and crypto guy. In this picture, basically, is showing this guy bragging about how cool his house is and how secure this front door, 4-foot thick titanium. And then you see a guy in black climbing in through the window. So that's basically just trying to understand your problem. So you think you might be secure, and then there's something totally obvious that's just staring you right in the face that could be a problem. This is akin to leaving your front door key under the front door mat or underneath a rock. So what we're going to look at, some attacks against access control devices, biometrics, authentication tokens, which I have a special place for in my heart, as you'll see. RFID, the next talk, I'm not sure which room it's in, is about some security implications of RFID. So I talk a little bit about that, and then the next presentation with some other guys, I'm sure we'll go into some more detail of that. Network appliances, things that you might hook up to your network, crypto accelerators, access points, NICs, mobile devices that are used all over the place. So starting first with some authentication token type of stuff, biometrics. Everybody here, I'm sure, knows about biometrics. If you don't, it's simply just a way to analyze some sort of human body characteristic. Primarily, fingers is used a lot. Someone had just mentioned to me vein patterns and vein structure is starting to be used. Hand geometry, iris recognition, using some sort of body part as one piece, one factor of an authentication scheme, so you can prove you are who you say you are. And that's something that's biometrics has been kind of glorified in the media recently because of various terrorist attacks. And it's really something that people are starting to adopt without understanding the potential problems with it. And I say potential because it really depends on the products you look at, the implementations of the products. But we'll run through some stuff here. Biometrics are usually considered more secure than systems that just use a password because they say, oh, you don't have to write down your fingerprint because you always have your identification pieces. But as you'll see in one of the examples, fingerprints can be lifted, easily recreated into a gummy finger to basically bypass a lot of the fingerprint scanners. Pictures can be taken of somebody's face and then possibly manipulated, maybe to create a mask. And a voice can be recorded. I don't know if any of you guys saw the movie Sneakers back in the 90s, but when they patched together the guy's voice samples. That sort of thing are possibilities to break these systems. So biometric systems usually composed of two or three components. You would most definitely have your biometric reader, probably application software either running on a PC or some back-end server, which would be the third part if it's a larger type of system where you have a larger installation. So 2 or 3 components. I choose to look mostly at the biometric device side because that's the hardware side of things. There's many other people that can look at software side, look at applications, analyze that for security type of purposes. But the hardware piece is usually the least inspected for most products, which is my experience. So the main problems are that the storage of the characteristics could potentially be retrieved if the data isn't stored properly on the hardware, because a lot of times the data needs to be stored somewhere unless the manufacturer is storing some sort of hash of your fingerprint. Even that could be retrieved and possibly used in another system. There's somebody giving a talk on some pro openness, I think, tomorrow that discusses all of the pros of using biometrics and how this sort of thing isn't actually a problem. So that might be interesting to go check out. The other thing, too, is I really distrust glossy marketing data sheets when I go to an expo and I see people saying, oh, yeah, our product's the best, it's secure, we've had the best scientists look at our stuff. That really raises a red flag for me because it almost goes to show that they might not understand the security mechanisms of their product because nothing, obviously, is 100% secure. So some marketing say that they store a set of unique data points instead of an actual fingerprint. Which only does so good because if they store a set of unique data points and somebody retrieves that set, they could still use that set on the same type of system. They just might not be able to recreate the entire fingerprint to use on a totally separate biometric system. So not that great of security. Also, some characteristics of biometrics can change over time. So as far as convenience of having this security, I'm not really sure of having this mechanism. I don't know how well it would really work if you have to constantly update the database with new characteristics. Also, if your fingerprint's stolen, sort of gives a new meaning to hacking and digital theft. And this is something that has happened before, as people's fingers have been cut off by thieves who want to steal their BMWs that have a fingerprint control to start up their engine. So pretty frightening and something that has already started to happen. I couldn't imagine if somebody's trying to remove an eye for an iris scan or something. But with fingerprints, you get a finger cut off, you have 9 more. Somebody told me in one of my hardware hacking classes is that one manual of a biometric system said to scan 1 finger on each hand in case you lose a hand. So, I don't know. So all of this stuff leads to fingerprint cloning. Tsutomu Matsumoto did some research back in May 2002, and there's a good link to his paper on this slide. Basically, he came up with a low-cost method to create a gummy finger that could defeat 11 of the different fingerprint scanners he looked at of different sensing technologies 80% of the time. Every 8 out of 10 times he could defeat the systems, and that's a pretty good ratio. What he did in the short version is he picked up a fingerprint from a glass, so something like this. If I walk away, one of you guys could run up and grab my fingerprint, using essentially super glue fumes to enhance the image on the cup or on the glass. He took a digital picture of that, enhanced it in Photoshop to edit the contrast, turn it into a nice looking fingerprint image, printed that onto a transparency, and then went through the basic steps to make your own printed circuit board. And one of the steps is to use a photosensitive PCB, which is just basically fiberglass with two layers of copper on it. Made his circuit board, and then basically used the circuit board as a gelatin mold, and then he has his fingerprint. And we have pictures of that on this slide, at least some of the pictures. So we see down here, this is already, his circuit board's been made, and for you guys, it's on that side. The circuit board's been made. He pours his molten gelatin, lets the gelatin cool, pulls off his finger, and now he has his fingerprint. The good thing about this is you can eat your fingerprint after you've used it, and there's no more evidence that you've done anything wrong. So an interesting thing is a lot of manufacturers, when this research came out, is they said, oh, but we have capacitive sensors. We use a different type of sensing technology than optical sensing, which was the first type of biometric system used. The problem is, even with capacitive sensing, the gelatin finger has the same sort of characteristics as a human finger, good enough for the biometric sensor to say, ooh, it must be a real human finger. So capacitive sensors don't solve the problem. RF sensors are something that's a little bit newer because they use an imaging of a deeper layer of skin. So I'm not exactly sure how deep, but apparently your fingerprints run a lot deeper than on the surface. So RF fingerprint scanners go a little bit lower. If you have a gelatin finger like this, it doesn't have the thickness. So somebody had mentioned to me, well, why don't we just create a big stack of fingerprints of the same identical fingerprint, stack it up, so you basically have a 3D gummy finger. Sounds like it might work to me, so might be some good future research. So authentication tokens, moving a little bit away from having a personal body part into some other piece of hardware that you own that you use along with a password to say, again, you are who you say you are, the classic answer to authentication in the first place. A lot of people use authentication tokens for storing some sort of private data, whether it's crypto keys, any sort of other user data, maybe even one-time password generation, something like an RSA Secure ID card. Secure Computing, I think, also makes a hardware-based product. So there's a lot of things out there. I'm going to talk about two authentication tokens, and this is some research that I'd done back in, early 2000. But I like talking about the classes of problems. Both of the devices I talk about, the Rainbow iKey 1000, the Aladdin eToken 3.3.3.x, which they told me was a prototype, have since been updated, and the technology has improved a lot. But these are great for introductory hardware hacks and just to see the horrible problems that have existed here. Basically, both research for both of these tokens let me essentially clone the device and gain administrator access to the device, thus logging into a system that wasn't intended for me. All the data on the device is stored in something called a serial EEPROM device. It's a typical memory storage device, a non-volatile piece of memory, commonly used in network interface cards and lots of products that need to store data in some way. The problem is most memory is notoriously insecure. There's no security mechanisms. There's nothing that says, ooh, don't let somebody read that device. So essentially what we did, read the serial EEPROM, learn what was going on, and fix that. And we'll go through the steps right now. So with the iKey, basically opening the device was a piece of cake. There was no security at all. There was two pieces of plastic press fit together. All I had to do is take off one little metal tab, use an X-Acto knife to pry the board open, or pry the case open and take out the circuit board, which looks like this down at the bottom, front and back. So as you can see here, there's some epoxy over the chips, which is a good security mechanism. Sometimes it prevents people from at least easily tampering with your product, even though there's many ways to get through epoxy that I've talked about in other talks. And one of them, if you feel like trying, is using a Dremel tool with a wooden skewer, like a shish kebab skewer. For some reason, it seems to work pretty well. Or use an X-Acto knife and just scrape stuff off. But basically, in this particular design, the manufacturer said, okay, we'll cover up the serial EEPROM, which contains all of the important data, with epoxy. The only problem is, due to the nature of serial EEPROM devices, which use a shared bus for all devices, this particular board had an upgrade port for extra memory. And there's 8 extra footprints there, and all of the lines I needed to read this protected device are available here. So I could solder wires to this part and read the device. So basically, the epoxy that I put on was a waste of money. Of course, the other thing I could do is just scratch off the epoxy and clip onto the device, which is another way I did it. So what I find out, this is what I found out. Basically, for the iKey, there's something called a master key, which is the administrative password. For these devices, there's a user password and an admin password, so the admin can configure these things without having to know about the user's password. Get full access to the device. In this case, we had a 256-character ASCII password. That was the maximum length. Its default, though, was rainbow, and that was documented in the manual. It says when you receive your devices, they'll be initialized to password of rainbow. So by some trial and error, and I show you a little more on the next slide, it turns out that the password was MD5'd and then encoded in some sort of way to create this obfuscated M key, this 8-byte value that was stored in the EEPROM device. And we could take advantage of that. Basically, here's how it worked. Through a lot of trial and error of using some of the development tools that came with the iKey device to set different passwords and see how they were stored in the EEPROM device, and taking some educated guesses about MD5 just because it happened to be, this was actually one portion of it. Just taking some educated guesses, trial and error. Turns out that we figured out this is what they were using for their encoding. XORs are not encryption, and somebody at one of my courses said XOR is usually referred to as encryption because it's total crap and it's reversible. And it's not encryption, though a lot of security vendors just think it is for some reason. So it was XORs, and basically what we were able to do is create any value, either create any administrator password we want or retrieve that administrator password that was stored there, run it through the XOR operation, and get the actual MD5 back. So the eToken is another device. I'd looked at these both at the same time to sort of compare what the current state of the art was. Again, we were able to get full user access to the device, and the link to the paper goes over in detail what I talk about here. To open the device, similar type of thing. The unit was made of 2 pieces of plastic, except in this case, Aladdin had actually glued the 2 pieces together. So you couldn't just slide an X-Acto knife through it, pop it open like the iKey. In this case, we used a heat gun to melt or soften up the glue that was used, and then use an X-Acto knife to carefully open one edge, and then open up the board, open up the unit like a clamshell, and take out the circuit board. One advantage here for us is that one thing I tell people who are designing hardware now is if they do use a product like this, try to get a low melting point plastic, so if somebody tries an attack like this with a hot heat gun, the plastic's going to melt before the glue does, and it will instantly become obvious that somebody had tampered with the hardware. So again, EEPROM device is on there, a different type of EEPROM device, different type of Cypress microprocessor, but I could still attach directly to the EEPROM and read it and write to it at will. So here's a little memory map that I put together during our research, and it turns out, again, you have a user pin, except in this case they call it a pin and not an M key or not whatever the user password was called. There are pins here, user pin, administrator pin, 8 bytes each. And then there's the default pin. So that's the default, again, when it's initialized and you get it from the manufacturer. Default pin was something. I don't remember exactly what it was, but you'll see why it doesn't even matter. Actually, well, it does. It was written in the manual. I just can't remember what it was. And here's what happened. Basically, by reading the EEPROM and using the development tools, again, we could change the user password, user pin. We could change the admin pin and experiment and keep reading the EEPROM and see what values changed. And what we noted is that these first 8 bytes changed when we changed the user password. The next 8 bytes changed when we changed the admin password. This default pin string thing, which we didn't know what it was at the time, never changed. One thing that gave me a clue, though, when I was reading this device, is there's 8 bytes here, 8 bytes here, 8 bytes here, 8 bytes here, and then all Fs. And all Fs is usually an unprogrammed area or an unused memory area. So I started thinking, okay, what's this extra 8 bytes for? It's obviously for something. We didn't run through the same process as we did with the iKey to see how things were created. Instead, we just copied the 8 bytes down here into the user pin area, and lo and behold, we could enter the default password, and we could get into the device. So that was just sort of a dumb luck trial and error thing. We didn't really have any expectations. It just happened. The Dallas Semiconductor iButton is another fun little toy. Another authentication token. The cool things about these are they're extremely rugged. They're used a lot by the U.S. Postal Service, uses them to keep track of their postal workers on their different routes. A lot of security companies, physical security companies, use them to keep track of their security guards throughout a complex or throughout some sort of environment or campus to make sure they've gone around to everywhere. And basically what they have is these devices. Each iButton device, there's multiple families that I'll explain in a second, but each device has a 64-bit unique ID associated with it. The unique ID isn't a secret because it's printed right on the lid of a lot of the devices, but that's what they use for tracking and for identification, just so they'll know, okay, postal worker went to all of these mailboxes, plugged in his reader, made contact with all the different tags, and they could trace his route. The iButtons, another reason why they're cool is they use something called a one-wire interface. This is the custom interface created by Dallas. It's actually 2 wires, but they say 1 wire because it's clock and data on the same line. It's a serial interface, and then it's a ground wire, a reference voltage of 0 volts. The device is parasitically powered, so it also gets power from the clock and data lines. There's no internal battery for most of the devices. Now, there are a number of different families of the iButton device. There's a Java-based crypto one that's really cool that I don't talk about here. And there's a number of other devices that I don't talk about. The one I do talk about is the DS1991 multi-key. And the reason I picked this device is, at the time, it was the only one that I could obtain in small quantities that had anything to do with security. And this one basically has 3 48-byte areas inside the device that are password protected, and you can use 3 different passwords to protect each of the individual subkey areas and store data there. So sort of a cool little device. Turns out that these devices are commonly used for parking meters in Brazil and Argentina, I think. I also heard something about them being used in Finland, where the cache value or some sort of identification value is stored in that subkey area. So sort of neat. If you have the right password, you'll receive the correct data. What the marketing sheet said is that if you have the incorrect password, you're going to receive some sort of random data sequence. So their intention was to prevent attackers from looking at the return data string and instantly knowing if it was a valid or invalid response that came back. Because a lot of times it would be easy to determine if the correct password was correct if the data stored in there is ASCII data and it comes up with some ASCII string. But a lot of times you can't really control what a vendor is using these devices for, so it might be some non-recognizable string. So this was supposed to thwart the exact attack that we actually take advantage of here.
Does it have any kind of random number generator embedded?
Sorry, say that again?
Does it have any kind of random number generator embedded or any kind of...
Does the device have any sort of random number generator embedded? To my knowledge, no, and you'll see why. And that was actually one of the things where, before I even attacked the device, I said, okay, knowing the technology of the one-wire interface, knowing that it's parasitically powered, it doesn't have a lot of computational power, could it really have a random number generator? If it has a random number generator, how good is it? Because it's still designing good random number generators is a hard problem. So I sort of assumed right off the bat that something was a little weird there. And then, of course, with my mistrust of the marketing data sheets, it sort of confirmed that. What I used is something called the iButton Viewer, which is a free tool. You can sort of see where I'm heading here. Is a lot of these devices come with free development tools that we could use to analyze the products. So I used this iButton Viewer, experimented with this DS1991 device, and realized that this random response isn't random at all. It's completely and totally based on the input password. So here's a picture of a screenshot. There's 2 subkey areas that I entered, hello. And if it was a truly random response every time I entered an invalid password, this data would be different. But it's not. So I said, okay, what I'm going to do is try to find out how this response is created, and then basically just do a dictionary attack of tons of different words and brute force style attack. Compare the response coming back from the device. If it's the response for the invalid password, then I know that that password is incorrect and move to the next one. So it's sort of a backwards thinking of like if we were cracking Unix passwords. I don't even know if you can do that anymore because haven't looked in a long, long time. But if you had your password file, you'd have your dictionary attack, run crack against it or whatever, create a hash and compare that. We're sort of comparing against the invalid response and not a valid response. So turns out that the way they create this is based on the input password, as I said, and a 12K constant block of data. And this data is constant for all of the DS1991 devices all over the world, everywhere. And I'll show you briefly how we figured that out. Again, there's more detail in the actual file that we wrote about it. So as I mentioned, you can basically pre-compute the 48-byte value that we'd expect for an incorrect password. If that value doesn't match what the I button is returning, then the data must be correct, and the password must be correct. So what we did to figure this out is we using, again, the SDK that came with the tools. There was also an API. We could write our own little applications that would interface with the I button through the serial interface. So we wrote a program that just ran through every different byte for just a single character password, and noticed that a unique 48-byte response came out. The first thing I always try is using XORs. Turns out that every character had a 48-byte response, and for multiple characters, the second character was shifted over by 1 byte and then XORed, and then the third character was shifted over again and XORed. And basically, it was just, again, trial and error. And I don't have a picture of what the algorithm looks like, but in the advisory, there is some information there. So that was sort of cool. And the scary thing about that is, since this constant block is constant for all devices, if somebody was really determined and wanted to break the Argentinian parking meter system, they could get a bunch of these devices, do a distributed style attack like this, where give everybody a finite word set, or a brute force. Okay, Joe, you run these things. Jim, you run these. And just keep running the attacks until you get the valid response, and then the system's broken. And then you have this problem of the DS1991 devices being everywhere, the readers being everywhere, and these passwords being everywhere. It's a hard problem to solve at that point. RFID. We'll look at the next few slides again. Check out the next guy's talk. Sorry, I can't remember your names if you're in the audience. RFID, for those that don't know, basically a generic term for any sort of non-contacting technology that uses radio waves, that uses radio frequencies, RF, to automatically identify people. It has been available for a while, but like biometrics, the media is starting to pick up on it. Think it's a great new technology, though they might not fully understand the security implications of that. The most common use, though some might argue with me, is to just store some sort of unique serial number on a data or on a tag, or maybe read a unique serial number from a tag that's pre-programmed, sort of like an I button that has a unique ID associated with it. That's usually stored on a microchip that's attached to an antenna. That combination of antenna and microchip is called a transponder or a tag. Usually an RFID system, like a biometric system, you need a reader of some sort, and then you need one or more tags. There are two major tag types for RFID. There are other sorts of tag types that are kind of hybrid versions, but these are the most major ones. Passive is the most popular because each tag doesn't have to contain its own power source, doesn't have to have its own transmitter. So the devices are cheaper, but they have a shorter range, shorter read range. Active devices, power source is included, so it's usually some sort of onboard battery to power the transmitter. And it has a longer range, which is an advantage. I think the demonstration that the guys are giving next, they're actually going to show that even with passive tags, they can be read from 50 meters away or something ridiculous. So even passive tags, without having their own power source, are at risk from far away. There's 4 different frequency ranges. Low frequency are the most common ones, and that's what I'll talk about here, 125 or 134.2 kilohertz. High frequency is starting to be used a lot for tracking, package tracking and things like that, because you can make the tags thinner and flatter and stick them on the side of things like stickers. With the high frequency range, there's also a number of ISO standards. So multiple readers and multiple RFID vendors conform to these standards, and then you can interchange tags and readers from different places. With the low frequency devices, that hasn't happened, and it probably won't because a lot of the vendors are trying to push high frequency. So low frequency, you need to have the matching tag for the matching reader for that particular vendor, and you'll see what I mean. So here's an extremely simple version of how RFID works. Essentially, the reader's antenna will transmit RF energy, which is received by the tag if it's within range, then is parasitically powered, again, powers up the circuitry, or I guess inductively powered, powers up the internal circuitry of the tag. The tag modulates the electromagnetic waves from the reader, and then the reader will demodulate the waves and convert that back to a digital signal that is then used. And this picture is actually a mobile speed pass device, which is actually a Texas Instruments digital signal transponder tag, a DST, that we talk about in the next slide or two. Inside, you can see this is just the plastic sheath for it. Inside, on the left side, left side is the antenna coiled around, and then you have your little circuitry on the right side. And for you guys over here, left side, you have your antenna coiled around, then your right side is some of your circuitry. So really small devices. Here are two different pictures that I thought were sort of fun. The top one is an RFID reader module that I'd actually designed specifically for hobbyists and for people who wanted to experiment with RFID. It's based on the EM microelectronics style of tag, a certain style of tag, the EM4100 family, which is a standard read-only tag. So this reader will only work with EM microelectronics tags. The bottom device here is a part of a development kit from Texas Instruments. The bottom one here, you have the antenna and the circuitry. That was to read Texas Instruments' version of the low-frequency 134.2 kilohertz tags, which just happens to be the same type of tag that the mobile speed pass device uses, same type of system. And that's what you see here, a mobile speed pass device. This picture I took a long time ago, and I was trying to experiment with the challenge response scheme of the DST device. So there is really no security between the tag and the reader. Sort of think about like unencrypted 802.11. It can be monitored, or if you have the reader for the correct tag family, the correct frequency, you can communicate with the tag. There's no authentication for the actual interface at all. If you're interested in putting together your own RFID system, you can do that, either with the Parallax module that I designed or the TI. Has a number of different things. Also, Make Magazine, which is a really cool magazine about a lot of do-it-yourself, hardware hacking, mechanical hacking type of stuff, is going to have an article, some stuff I put together. That should actually be issue 4. We pushed the article back. Issue 3 just came out. So here's talk about a little bit more about the DST device, because that's the RFID device that has the most security component to it, the most interesting for us, I think. So the DST tag in January 2005 was actually cracked by some researchers at RSA. It was basically a challenge response scheme that they ended up reverse engineering from a single slide that apparently came from some German conference somewhere that was just stuck on somebody's website that they'd pulled down and found a block diagram of the cipher. As most of you know, in security systems, you shouldn't rely on the secrecy of the cipher for security. You should rely on the secrecy of the key. In this case, all the researchers had to do is reverse engineer the cipher based on that slide they found, and they ended up breaking the system, and they could actually emulate these tags, use them to get free gas. They're actually used a lot for vehicle immobilizers or to start and stop engines in cars. McDonald's used them for a while. We're experimenting with them. So the big problem is there's 150 million of these DST tags out there that are used for various security-related applications that can now be cloned or spoofed, and someone might end up getting free gas in your system and things like that. So I'm not sure what Texas Instruments' response was to this, but it seemed to have made the media for a few days and then just dissipated, and people, I think, are just using the tags like nothing ever happened. The Intel NetStructure 7110 was originally known as the iPivot iPivot something. The company ended up getting swallowed up by Intel. Basically, it was an SSL crypto accelerator that, in case you don't know, was used to offload some of the cryptographic functions from the primary web server to an external piece of hardware to speed up performance, speed up all of the traffic handling. It turns out that this device we'd actually rented a few years ago. A customer was interested in implementing some crypto accelerators, so we'd rented a few devices to take a look at them. This one was the most tantalizing for us because it had a bunch of screws on the top. All we had to do to get access to the device was open up all the screws. So we didn't have to actually mess with anything at all, which meant we could be careful. If we were careful, we could open up the device, do what we needed to do, close it back up, and return it to the rental place and not get in trouble for it, which we did not get in trouble for. So this device was a standard rack mount piece of equipment. It ended up having a standard PC motherboard, which was cool. It was a Pentium 2, and it had just a PCI-based accelerator card plugged right into it. So it was in the era of creating products quickly and using off-the-shelf products, which made it a lot easier for us to launch our attack. On these devices, there was a serial port-based management console, so the administrator could just plug in with an RS-232 serial port, connect to the device, do what they needed to do to configure it. And you can see the down here, there's 2 ports on the bottom, standard DB9 connectors. So these devices, it turns out, can be compromised to allow supervisor access by taking advantage of that management port. We have the original advisory here, and then a chapter that I wrote that's actually available for free now that goes into some more detail of that, and we talk about it here too. So in this case, we opened the unit, unscrewed all of those screws on the top of the device. Turns out that the file system wasn't running off of a hard drive. It was running off of a compact flash card, 32 megs, which is convenient. Took that compact flash card, inserted it into another system, made an exact image of it using DD, ran strings on the resulting image, and figured out that it was actually a BSD flavor of Unix. There were some strings in there that said, I am BSD, essentially. So we knew from that. What we could do at that point is mount that file system to a spare machine. So at this point, we weren't even touching the actual compact flash card anymore. So we could put that back. We didn't want to tamper with it because then we could have potentially damaged the device. So we used the image of that, took a look at the file system and realized, okay, there's a few commands on here that aren't standard for a BSD installation. One of them was this password generator. I forget what the file name was called, but it stood out from standard Unix type of file names. Turns out that this password generator actually created the supervisor password, the administrator password for each crypto accelerator box based on the MAC address of the unit, the MAC address of the network card, which is not a secret, which is usually printed on a label somewhere, or can be determined other ways. So for any box that was available, we could now find the MAC address, create the administrator password, and log into the device. So the reason that this attack was relatively easy for us was because this design was based on the standard PC architecture. There wasn't any sort of custom design going on. So we could easily say, okay, take out this compact flash card. It didn't have some sort of custom file system on it. So we could easily take a look at that, mount it onto another system, DD it, do our research on that. Another thing which was really helpful is the executables that we were looking at were compiled with the debug symbols turned on. So running it through IDA Pro was pretty nice. And then the final nail in the coffin was the crypto routines that they were using inside of these executables, inside of the program used to create the password, was extremely weak. I can't remember if they used XOR. They probably did. But details of that are in the advisory and in that chapter. So Cisco routers, this is one that is arguably maybe not a security problem, and people tell me that it's not really a security problem. But what do I know? I'm just talking about it because I think it's a security problem, and if you can get access to the device, it sounds like it's a security problem to me. 3 different types of passwords that Cisco routers use: a type 0, which is the plain text, type 5, which is MD5, and type 7, which is this encrypted version. It turns out that the password in this type 7 format is created by an XOR against a constant block, against a constant value. This encrypted password is stored on the router in the non-volatile RAM. You can retrieve it through various commands of the configuration settings and determine what the original ASCII password is. So here's the actual constant block that they use in ASCII. So we'd look at the hex equivalent without the quotation marks. So the example here is, let me see if I can actually remember what this is. Oh yeah. So this is the encoded version. 8 is our offset into the constant block. Our first byte here, 8, that's the offset, so we'll go 8 characters in. And then this first character, which looks like it's 20 hex, that's XORed against whatever hex value is in the constant block that we've offset to. And then we use that point and start moving forward, XOR 4E with whatever the next value is, and then we come up with AB, which was our default, or which was the password. So that's the Cisco router. The 4758 secure processor is not something that I've actually experimented with at all, but I wanted to put it in here because it sounds really cool, and because it is probably the most secure coprocessor system around. It's used a lot in financial and automatic teller machine infrastructure, banking transactions, things like that, and it sounds really cool, and it actually contains a number of tamper-responsive sort of features, anti-tamper mechanisms, things that I talk about a lot that most vendors don't actually design into their products because it costs too much. These guys, IBM, actually did design some of the tamper protection and crypto support, I guess, and the tamper protection into their product. It was really cool to read about. This device also has some true random number generator. I think it's true, probably as true as we'll get for now. Authentication. It also has a general purpose processor, so some custom applications can be written for the device. In 2001, some guys in the UK actually figured out an attack against the 4758 by taking advantage of some of the software that came with the device. So it wasn't entirely a hardware-based attack because they were actually taking advantage of some software, but it was definitely an interesting attack, and they could extract some of the DES keys that were used on the device. So take a look at the website for more. There's actually a few different types of keys stored on the device. So depending on what you're looking for, I guess some of them are more important or cooler than others. But it seems interesting that they can actually attack a device like this, which looks like Fort Knox, with this secure envelope on top of it, which is an anti-tamper mechanism that you're not really allowed to even X-ray. If you X-ray it, you are not going to be able to see the components inside. It's encased in epoxy. So they ended up breaking that just based on a software flaw, which has since been fixed. So with somebody with physical access to the system and an FPGA development board, so they can create a way to determine the DES keys, they could break the system. Access points. Everybody knows about access points. The reason I picked this one is the Dell TrueMobile 1184, one of the many available. The interesting thing about this is this is based on an embedded version of Linux. And a lot of devices nowadays are starting to use Linux as their core operating system and things like that. So this is just one example that we talk about in the hardware hacking book that all of you guys probably got in your bags. It turns out if you hook this thing up to your network, do a port scan, you'll see all of these open ports, which are telltale signs that it's a Linux type of device. If you telnet into port 333 with a default password, which is root admin, you can gain complete control of the device. So it's sort of cool because now you have this low-cost Linux-based platform. And there's tons of other devices out there that are either running embedded Linux on purpose or where people have ported Linux to the devices. And visit those sites. There's a lot of cool things going on. People have ported Linux to the iPod and to all sorts of other things. I think a lot of times for no other reason just to say I ported Linux to the iPod, which is cool, and that's a perfectly fine thing to do for a hardware hack. Sometimes it doesn't have to be a reason or a goal. So the interesting thing about this access point is you don't need any special hardware tools. You don't need any reprogramming skills. All you have to do is connect the thing up to your network, telnet in, and you have a nice little Linux platform. MAC address cloning. I'd mentioned that that network interface cards store MAC addresses on double EEPROMs. At least I think I did. Maybe I didn't. Anyway, they are. The same sort of device that was used in the authentication tokens that we can easily just clip onto or solder onto, connect up to a standard device programmer that you could probably make with $10 worth of parts, or you can buy a more expensive one and read the data right off of it. This link here is to a little paper I wrote a long time ago about modifying network interface cards to clone the MAC addresses. And a lot of software tools use the MAC address as a copy protection scheme to only run on devices with a network card with that particular MAC address. So you could clone the MAC address and use software on another machine. Possibly gaining access to MAC filtered networks, people who have MAC filtering set up on wireless networks, for example. And depending on the network interface card that's used, you can access other configuration data that may or may not be useful if you're modifying the double EEPROM device. There are also tools available depending on the NIC card and depending on the platform you're running on. You can change or spoof the MAC address in software, but that's not as cool to me as actually modifying hardware. So there's a table here that's a list of some of the manufacturers that I've looked at of NIC cards and their model numbers, and basically the double EEPROM device they used, MAC address, and then how the data was actually stored in the double EEPROM device. Some of these devices you could just program a new MAC address in, and you're good to go. Some of them you had to program a checksum in as well. How to calculate the checksum? Well, that's usually detailed in the data sheet of the Ethernet control IC that's on the network interface card. So you take a look, see what the main processor is, pull up the data sheet, and recreate the data in the EEPROM. So we're just taking advantage of common tools and common documentation that a designer, that a developer would need to know how to put the data in correctly. So moving on to mobile devices, PDAs, something that I experimented a lot with, especially Palm-based devices I thought were sort of fun. Some of the current risks, I'll briefly run through these, is that portable devices nowadays are being used for business use, for personal use. A lot of people now have the Palm Treo phone, which of course they're going to have their personal contacts in and their business contacts. They might receive their business email through the device. So a lot of people are mixing business with pleasure, which I've learned through my days you shouldn't do. Most of these portable devices up to this point have no security framework. There's no access control, no data or memory protection, meaning one application could easily access another application's data. Any security mechanisms that are available are usually either weak or flawed. Of course, this is a generality because I haven't looked at every single device out there. But the ones I have looked at, security mechanisms that exist don't really exist because you can bypass them. Some of the always-on technologies that are now just totally pervasive everywhere, Wi-Fi, Bluetooth, infrared, those things that are on all the time means that somebody could attack you all the time through some sort of flaw if there is one. External memory cards are common on a lot of portable devices now for external data storage, especially now that portable devices become more powerful. People are storing images and movies and MP3s. So there is external memory card support in the devices that could actually be used by an attacker to load applications possibly onto your device and execute immediately without any sort of confirmation, which is sort of pretty cool. And the other thing is external memory cards are easy to steal. So from a security point of view, you don't really want to store secure stuff on that device. Except some people will argue against me and say, oh, well, you should store your crypto keys on a secure memory card or on an external memory card because then you can keep that with you at all times. So you could potentially do that as long as you don't lose that. I'm going to just run through some Palm OS stuff. As I mentioned, I enjoyed analyzing the Palm devices. We do talk a little bit about Pocket PC. Palm system passwords for OS versions less than 4.0 use a 32-character ASCII password at a maximum. And it turns out, based on some research of looking at one of the PC-based HotSync Palm desktop applications, that they were obfuscating the system password with an XOR and a constant block. So again, XORs everywhere. Some details of that is in that link there. Basically, this obfuscated version of the system password can be retrieved either through a hot-sync operation. So if somebody is synchronizing their device either through serial port, infrared, network, you can pick up that password hash, run it through the reversible obfuscation, and pull out the ASCII password. You can also get it off of the Palm device itself. So if somebody leaves their Palm device on the table, somebody can instantly go up, suck that encoded password block down, and decode it, and then gain access to the device if it is locked. But you'll see why even if you have a system password and you're locking your device, there's another way in, which is even more scary than this. Also on a PC or on a Mac, you can also get this password hash. It's stored all over the place. For devices greater than 4.0, you still have a 32-character maximum password, but now they're using MD5, which, as we know it, is not reversible. This using MD5 was directly in response to some of the security advisory stuff that we had done. Palm was not very happy at the time with our information. And we sort of felt, at the time, it was sort of, we felt it was a responsibility to let people know about the issue after, of course, going through the full disclosure process and all of that. Because a lot of people are using Palm devices as a secure device. They were using it for security purposes, even though the devices weren't secure. Was there a question somewhere?
Yeah. So the password remains 128 bit MD5 hash. It's also combined with a sub before doing the hash, or it's just a straight hash for the password?
Is the encoded block just a straight hash of the password, or is it combined with some sort of salt? As far as I know, is a completely just straight hash. So, and that's what leads to the fact that we can just run a dictionary attack against the hash. And because of human nature, PDAs, people hate writing long passwords. It's hard enough to get people to use long passwords and secure passwords, or more secure, not just common dictionary word passwords on a PC. It's nearly impossible to get people to do something other than a common short password on a PDA, because no one wants to enter other characters, alphanumeric characters, exclamation points, and things like that, because it's a pain. So we can take advantage of that, advantage of the fact that people like using short passwords, that people like using common passwords. Just run a dictionary attack against the hash.
My question was because if you have a sal, household combined with a password, you have to do a calculation on the fly, okay, for each and every password that you want to have. But if they don't use a sal, you just have to calculate all the possible passwords, all the possible combinations, store them on the CD, and then just do a lookup.
Right, exactly. So if you have the salt, you have to calculate the entry every single time. If you don't have a salt, you could basically create MD5 hash of word list, which probably people already do. You can just buy the CD of all of the MD5 hashes and just let it run. So the POM backdoor debug mode is the reason why it doesn't even matter if you have a system password, because we can blow right by it and gain access to the system, even if it's locked, if the device is locked with a password. So the debug mode is actually something that was documented, created by POM for developers to run applications on actual hardware while they were developing the system. It turns out we can take full advantage of this to install applications, delete applications, view raw memory, which is one feature that I ended up using to create a forensic analysis tool, an imaging tool for POM devices. You can export databases so we can suck out information, whatever we need. The interesting thing is that no notification of the debug mode is actually enabled on the device. So if we enable the debug mode, even if the system is locked, we suck out the information we need. The user will never know that we've just attacked their device. Pocket PC, similar sort of thing where they use, again, you guys see XOR against a constant block to protect their system password that's transferred through the ActiveSync interface. I'm not sure if this has been upgraded. I think this was for ActiveSync 3.0, so I'm not sure how old that is because I don't have a Pocket PC device, but I'm going to guess it's fairly old. Hopefully they've upgraded the way that they're storing password hashes. Password hash, not only is it stored on the device, it's also stored in the PC registry. On some devices, there's also a 4-digit PIN that's used for other sorts of access. 4-digit pins, 10,000 combinations, doesn't take that long. And there's actually no sort of a maximum attempt count for these systems to say, oh, you've already tried 10 times, you're not allowed to do anymore. So we could just run through 10,000 combinations. It doesn't actually take that long if you're sitting in front of the TV, you're drinking beer or whatever, as long as you don't forget what number you're at. It actually goes by pretty fast. And this is something that anybody who has experimented with locked cell phones back in the early 90s or late 80s, that all use the 4-digit PIN to lock the devices. Fairly easy to do, extremely easy to do. Pocket PC registry, the registry actually on the PDA itself can be accessed using a few tools by any user on the device. There's no protection, just like in Windows, sort of. If you're an administrator, you can get right in. And you can also change this something called a control panel applet, a CPL, in the registry of the Pocket PC that normally points to the password screen. So if you enable locking the locking screensaver password type of thing on a PDA, you can redirect that to another application to bypass that question, that security mechanism. And thanks to Microsoft, it's actually documented in one of their application notes on how to do that. So .NET Debugger is actually what's used to create Windows CE Pocket PC applications. Like the debug mode on POM devices, the .NET Debugger can also be used to access the registry, install applications, all of the fun things that developers need to do, but now attackers can do the same thing, and that's the problem. The phone edition, a few additional problems. XDAdevelopers.com, a nice group of people working on a bunch of research related to the XDA device, which is an OEM version of a Pocket PC that's popular over in Europe. These devices have a diagnostic port that could be used to obtain certain information, to erase the system password. Could also be used to execute code directly from a memory card. And here are some interesting screenshots from Joop de Haas, who gave a talk about this at Black Hat Amsterdam 2003. So some configuration and test information on those devices that could potentially be used. I'm going to quickly run through this because I do want to leave time for some questions. Some advanced attacks, some advanced hardware attacks that are really starting to become more popular because a lot of this equipment that's used for dye analysis, for silicon dye analysis, is available in academia, in universities, in some laboratories. If you're lucky, you can get access to this equipment. And now there's also services available that somebody like you or I could actually go and give money to and get some results back. So you don't actually have to own the equipment anymore. You can essentially pay someone else to do what you need. Basically, chip decapping, dye analysis is gaining access to the actual dye of the integrated circuit, of some sort of memory component, of some sort of FPGA, some sort of processor, analyzing that dye to either get some sort of data from the device, maybe repair a security fuse that's been blown to allow you to then read all of the data out of a chip, and using common tools that are designed for IC designers, for chip designers that need these kind of tools to do their rework, to do their repairs and analysis. X-ray is another fun thing that could be used for attacking devices of any type. Basically, my favorite example is this thing down here, which is an old expansion board for the Pac-Man video game system, the arcade game. This expansion board was to turn the game into Pac-Man Plus, and Bally Midway, when they released this, wanted to encrypt or some way protect this circuitry so somebody couldn't go reverse engineer it and sell unauthorized version of the Pac-Man Plus. So it turns out that this thing was actually totally encapsulated in epoxy. And one guy, Clay Cowgill, who was a big classic video game fan, had tried to get access to this so he could reverse engineer it 20 years later and just provide the mechanism to people so they could understand what was going on. He tried everything to get through the epoxy with heat and knives and microwave ovens and everything to get access, and he just couldn't. So he decided to bring it over to his friend who worked at a veterinary school, stuck the device in the little pet X-ray, and came up with the X-ray image, which looks like that. So from this, he could actually see, okay, that's the microprocessor, just from some educated guesses, because it's the biggest part. It turns out it was a Z80 microprocessor. Here are some other logic chips, and he could actually visually reverse engineer what was going on at that point to figure out the mechanism used, and he did. And now we can all play Pac-Man Plus on our emulators thanks to him. So to finish up, just some common hardware problems that we'll run through. Most design engineers aren't familiar with security. I can say this with a large amount of confidence because I am a design engineer and I've given talks at engineering conferences. And most engineers want to design a product, get it working, get it out. Because of the short time to market, because of pressures from management, it's hard to design in features that arguably aren't useful. Of course, security mechanisms are useful, except a lot of companies are just willing to bear the risk of an attack and maybe just pay money later if something happens. And that's common with the software industry too. Is people want to get software applications out there. They say, oh, we'll add security later, it's okay. And then they get broken and it makes the news and the company loses a lot of money. Anti-tamper mechanisms aren't really used. As you've seen, it's easy to open up all of the products that we've talked about here except for the Pac-Man Plus. You can probe the circuitry, do what you need to do with no major problem. A lot of designs, a lot of products are based on publicly available reference designs, which are essentially designs created by manufacturers to make it easier for developers to integrate the ICs, the components, into their own design. So it's essentially a pre-made system. So if I was going to maybe work with the Broadcom chipset to make a cell phone, I could call up Broadcom and say, hey, do you guys have a reference design for a cell phone? And they might say, sure. They'd send me their reference design, which might be an actual hardware board with schematics. And I'd have a pretty good idea of how the system works. The thing is, a lot of people do that and then build their product around a reference design. So if I can also identify the reference design, I now have a leg up on reverse engineering the design. Components are easy to identify because you can look and see the part numbers on the boards, which a lot of times The part numbers are there for manufacturing convenience, but they're also there now for our convenience to pull up data sheets and pull up information on the parts. Improper protection of external memory. I probably don't even have to say this anymore based on our examples. But there is no really good security for memory. Even if there are security bits in place, using those advanced attacks with analyzing the IC dies doesn't really do that much good. You can pay somebody $50 to decap the chip for you, and you can start analyzing at will. And then security through obscurity is still practiced in this industry, hiding stuff, hoping that an attacker doesn't find it. Obviously, hiding something doesn't make the problem go away. It takes one person to find the problem, and then the system's blown wide open. And finally, conclusions. Even though some of these examples are a little bit old, some of them are not as old as others, same classes of problems still plague the hardware if you look at newer devices. So hopefully this has at least given you some sort of idea of what's out there as far as hardware attacks in the past, and maybe you can apply some of this stuff to newer devices, which I hope you do. And don't just blindly trust hardware. It's not voodoo. It's not some secret. It's just something that a lot of people don't quite understand yet. And hopefully at conferences like this, now we'll start to understand what's going on. And that's it. So thanks. Hopefully we have time for some questions. There's one.
You talked about the Pocket PC phone editions. Have you looked into any Symbian phones?
Have I looked into any Symbian? Is this thing still on? Okay. Have I looked into any Symbian phone types of products? I personally haven't. The only sort of Symbian platform I've looked at is the Psion device, which I don't talk about in this, but on my website I actually have a paper on some mobile device forensics. But the newer Symbian devices I haven't looked at, but I am hoping people are.
I was just curious if you run into any Symbian seems to do the code signing based on hardware versus the
Right.
based on registry.
Yeah, Symbian seems to do some code signing in hardware, and that's a good thing because as newer devices come out, I think vendors are starting to realize some of the problems, but I haven't looked at that, though. Another question? Any comments about proximity badges, the HID type? I forget I think they're Wiegand stripe cards or something, where you have there's some sort of like magnetic strip inside of the device. I haven't looked at them personally, but I think it's the same sort of problem as like a mag stripe. If you have the reader, I don't think there's any sort of security there. If you have a reader for proximity cards, you could just walk up and read somebody's proximity card. As far as cloning the device, I don't actually know, but I'd assume it would be possible to just maybe slice open a card and try to rearrange some of the bits. I'm just guessing now, but it might be worth a try. Orange. What version of Cisco router was the encapsulation on? I think it's all. I think all Cisco routers use them. Yeah, even now, because somebody said that apparently it was used for some reason. They just didn't tell me what the reason was. Well, that's a good question. You've stumped me in the, somebody's answering, somebody said something that might be useful.
Do it the way VMS does it, Purdy over salt.
I heard part of it, but sorry. I'm staring at you, but I didn't actually tell you that I only heard half of that.
Purdy over salt.
Parody?
Purdy, P-U-R-D-Y.
Purdy over salt. Hopefully that means something to somebody. So, anything else? Another one in the back. How do you deal with Xilinx FPGAs as far as attacking them or securing them? Either way. Well, a lot of SRAM-based FPGAs, which I put a bullet here, but I didn't actually touch on it. FPGAs that run on that are SRAM-based, which are most FPGAs that are out there, require some sort of external memory that stores the configuration data that's then loaded in at power-up. So that type of device, you can, and actually conveniently, that configuration data is usually stored in a serial EEPROM. So you can do the same sort of thing.
They're starting to encrypt the screen when they want to download
Right. Well, they're starting to encrypt the stream. I haven't run into that yet. It would ultimately depend on what external type of memory device they're using. I know some of the newer devices that are flash-based, you don't have to load the configuration data from external memory anymore because it's flash-based, it's non-volatile. You pre-program it directly into the FPGA. I think a company called QuickLogic has some sort of gate technology called anti-fuse technology that's harder to probe even if you do decap the chip. But I haven't looked at the parts that actually have an encrypted stream.
Somebody has asked my question.
How bad is what?
Collision rate. How bad is the collision rate?
How bad is the collision rate for any of the scanners? I have no idea. Yep. Any products that implement code signing? Well, the Xbox does. Any papers on it? Actually, I didn't mention Bunny's work in here. If you go to, I think it's hackingthexbox.com, the Xbox uses code signing, and a lot of the video game consoles try to use code signing to protect or to prevent people from loading unauthorized code onto the systems. Xbox tried to do it, and Bunny ended up breaking the system, but maybe they fix it in the Xbox 360, but that might be a good place to start to read up on it. Oh, sorry. Right, right. Any vendors that are particularly good, other than Bally Midway, which did a really good job. Yeah, Research in Motion, the BlackBerry device seems to. That's one company that actually says we're a secure device, and they're trying to keep that. You know, they'll guarantee point-to-point security, but they're really focusing a lot on the mobile device side because they know there's people like us that want to look at the stuff. So they seem to be doing a really good job. And they're not paying me for that either. So anything else? You guys just want the book, don't you? Which I forgot all about. Who's the guy that asked about the MD5 hash stuff? Oh, he's gone. Let's see. Who else asked questions? I can't really see from up here, so it's sort of... Throw the book. Yeah, I don't want to throw the book. Let's see. Who is the newest in the security field? Maybe of those that ask questions. How many years have you been involved in security? Last year. Anybody else? Last time I gave a book away, it was the guy's first day, and he was sent to the conference. How many months? How many months have you been involved? 5? Oh, all right. You want the book? We're also doing a book signing later for some of the Steel and the Continent series of security fiction books and stuff, but hope you like it.